So this is week not for week 6, and on a Wednesday, and we are going to look into relative motion analysis, and we are going to focus on velocity first. Okay. A bit of good news. Okay, just to let you know, if we have a great distribution, and this is 60% of students that have been graded for the term test, this is 100%, this is 50, and this is 0. This is your grade. Okay, we are having this trend. Oh, not like that. Sorry. Okay, so this is good. Okay, a lot of you do your study well. You are here. Those that don't do enough homework, you are here. So that is a good news. So we have not completed grading yet. We are still grading at this moment. I have another question to ask you all. Are you having a big term test on Friday? When? What is it? Oh, okay. So tomorrow, okay, I will record my lecture. Are we clear? Don't come. If you have static, go and study your static. Are we clear? Okay, go and focus on your static. You all know the lectures are recorded, yes or no? Okay, so go and do your static. I will still be there, okay? But if you have to focus on static, go. Are we clear? Okay, I don't want you to be stressed out. You have to do well in static. If not, if you come to 3A, what will happen? You die. Yeah, he knows, okay? What's your name? Hey, Anj, can you come here for a while? Okay, Anj is, I'm going to embarrass him, okay? He's one of the top students in my course, okay? He unfortunately have done 3A already in summer, and now he's doing 2Q. Can you tell them more about 3A?
It's fun.
It's fun. Oh, shut up.
That's not enough. Yeah, and it's hard and fun.
Okay, so how to be successful in 3A?
Practice everything, like twice, thrice.
Yeah,
And during the exam, pay attention what in the exam.
and then does 2P, is 2P important in
Yeah, for sure.
Okay, so I'm gonna embarrass him. I know his grades. His 2P got an A plus. His 3A is close to an A, but he's not very happy. Thank you so much. Okay, so do well in 2P. Are we clear? Okay, then 3A, you will tend to like me more, or not 3A. Whenever I go outside and walk, I have to look behind my back because 3A has very high failure rate. Are we clear? Okay, I'm worried. Okay, not worried, but I'm being paid. I'm being paid a good salary to do two things. So I do two things. Anyone? I'm being paid a good salary so that my courses are life-changing and life-shortening. Are we clear? Life-shortening. Right. I want you to upload. If you go to Avenue to Learn, okay, I want you to I posted examples, okay, on Wednesday, and we will need that, but I need I need this example over here. I'm going to download. Hold on. Hey, where did the download go? Okay, I'm going to do this example today. Okay. And this example will highlight how simple this method is. We are going to start from a simple example first. Then we are going to do something crazy. Okay. I love crazy. How many of you love crazy? You guys are sad like me. But it's good. Crazy, okay? Right. So you can see over here, if the block C is moving downwards at 4 feet per second, we are going to determine the angular velocity of AB at the instant. Okay, so we are going to determine we are going to determine omega AB. Okay, we are going to determine our omega AB. Now, as you can see from here, right, the first thing we do, we put in our coordinate system. This is our X and our Y. This is our rotation about Z. So from here, we can also see that there are some boundary condition. Okay, from this diagram, we can identify boundary conditions. Okay, so what are the boundary conditions that we can identify for now? So the first thing we know that at point A, right, velocity at point A is equal to what? 0. Okay. So we have a situation. Why is it 0? Because at point A is in the condition of what? In. Okay, so velocity is at. Now, then at point C, we can identify another boundary condition. At point C, we know that velocity at point C in the x direction is equal to what? 0 meters or feet per second. And why this is the case? Because at point C is a what? Slider with restricted motion in the what? In the x direction. So what we are identifying now, what we are doing down here, which is important for this chapter, what we are doing now is we are what? We are identifying the boundary what? Conditions. Okay, we are identifying the boundary conditions. In engineering, whatever subject you do, okay, knowing the boundary condition is important. Now, one more boundary condition that is not so obvious is this, okay? So if we were to sketch a circle from B to A, hold on, I'll try this to sketch a circle. Okay, so I'm sketching this circle now. And we know for the fact, okay, this is important, okay, if you might miss up this. We know that VB will be coming down. And the VB will be coming down just in the what? This is not equal to 0. Okay. Whereas VBI is equal to 0. Okay. Now I want you to like hear me out in this, why we make this assumption. Okay, it's not just okay, we just gonna make this assumption. Okay, why we make this assumption. Okay, now if I'm going to draw a similar, okay, a similar structure like this. Okay, so at point A, we have a pin. Okay, and at point BC, we have a slider. Okay, so this is our slider. So as you can see, now our slider can come lower. Okay, and at this instance, we have this now. So this is our AB, and this is our BC. Okay, so this is our point C over here, right? Like what they have. And it's still the same. This is still coming down at 4 feet per second. Now this angle changes now, just arbitrary numbers. This becomes 15 degrees. Okay, and again, just arbitrary numbers. This is 30 degrees. Okay. So what we realize from here, the boundary condition, right? This is still valid where the velocity at A is still 0. Velocity at point C is still equal to what? It's still equal to -4, or in the x direction is equal to 0 feet per second. However, if we were to draw a circle that's around, okay, I'll try to center this, okay, all right. So what we realize that VB now, okay, we have a what? This is our VB. Okay. When that's the case, our VB will have two components. We have a VBJ, and then we have a what? VBI. We clear? Okay. You have a J component, and you have a what? You have a I component. Okay. So what I'm trying to highlight is this. The solution that we are providing happen at the instant shown. At the instant shown means what? When BC is at what? 30 degrees. And when AB is on the what? Exactly 0 degrees, or on the line in the horizontal plane. Are we clear? If it were to shift, then our solution will not be valid. You have to reformulate. Are we clear? Okay. So what I'm trying to highlight over here is at the instant. Sure. Means at that moment. Be clear. Okay. If the angle changes, then this solution that we are writing out will not be valid anymore. Okay, because of how we're going to formulate our solution. Okay, and I'll show you how we formulate our solution, why it's only valid in this situation. One of the reasons is what? We know that VBJ is not equal to 0, but VBI is equal to what? 0. Over here, we know that VBI and VBJ are not equal to what? 0. Okay, right. So we have identified our boundary condition. Okay, the diagram we're going to focus is on this one. Okay, we're going to focus on this diagram over here. So we know that first we have to, after identifying the boundary condition, we have to find